Hi, everybody, and welcome to part two of the chemistry of life. What we're going to try to accomplish today in the lecture is we're going to identify specifically what molecules are and how we're going to form them on the basis of electrons either sharing or donating. We're going to be looking at chemical bonds, again, differentiating the difference between covalent and ionic bonds, and then being able to see the differences between atoms and ions. So let's go ahead and get started. One of the first things that we need to identify are electron orbits. So just like we talked previously in our last lecture, we know that electrons are going to have a negative charge. Now we know that in the very middle, right here and right here, that's going to be our nucleus, and our nucleus is going to contain our protons with our positive charge and our neutrons, which have a neutral charge. Again, positive, and we have a neutral. Electrons have that negative charge. Now, because they're on the outside, they're going to be orbiting around the nucleus. And depending on how many electrons we have, it's going to tell us how many shells or orbits we're going to have. In this case, our hydrogen atom has a singular electron, meaning that it's only going to be in the first shell or first orbit. Our oxygen atom has 1 and 2 shells. Now, when it comes to shells, it's incredibly important to remember that electrons, they do exist in different energy levels. And the only way to have orbits or shells is the electrons need to take up all of the positions within that orbit before starting the second one. So in our first orbit, we need to have at least 2 electrons before we can move on to our second orbit. So again, each position has a certain number of spots electrons can take before it moves on to the second orbit. So again, they always need to be filled before it can move on to its next orbit. So when we're talking about those orbits, they're also going to be known as valence shells. Now, one of the really important things to understand when it comes to valence shells is they want to be as stable as possible, meaning that these atoms want to have as much electrons as possible to maintain stability. And when they're not stable, they're going to try to find other electrons in order to have that stability. So looking at this over here, what we're going to do is we're going to look at our hydrogen right here, our lithium over here, and then we're going to look at our sodium down over here. And what we're going to do is we're going to go ahead and see if they have achieved stability. So in this case, we have our hydrogen and we have our first orbit. Now we know that in our first orbit, we want to have at least 2 electrons in order to maintain stability. So in this case, our hydrogen is going to be looking for an extra electron in order to find its most stable form. Lithium over here, it's in its second orbit. In our second orbit, we want to have at least 8 electrons. So in this one, it's going to be looking for 7 more. Same thing with our sodium. It's going to be in our 1, 2, 3rd orbit, and it only has 1 electron. So it again is going to be looking for 7 other electrons in order to maintain stability. Now, if we go ahead and look at our group 17 over here, for fluoride and chlorine, we can see that this one is in its 1, 2 second orbit, and we have 1, 2, 3, 4, 5, 6, 7 electrons. So in this case, we have not achieved stability yet because we have 7 electrons, and it's still going to be looking for 1 electron to maintain its stability. Same thing down here. We have 1, 2, 3, 4, 5, 6, and 7. So we have 7 electrons, and we're looking for 1 more. And I'm sure you can connect the two, that in order to maintain the stability, this one can share or donate to this one in order to maintain that stability. So that's one way we can achieve that stability for these atoms. So that actually brings us to our next topic, which is how electrons are going to determine chemical reactions. And it's all up to the distribution of electrons between those atoms. Again, atoms want to be as stable as possible, so they want to find as many electrons as they need in order to achieve that stability. So because they're always looking to find that stability, they're going to end up binding and creating molecules. So a great example is hydrogen and oxygen over here, and in the creation of water. In this case, our hydrogen is going to be looking for an extra electron. So in this case, I believe our hydrogen is looking for 1, and then our oxygen is going to be looking for 2. So that's why we end up with something like 2 hydrogens, 1 oxygen, so we end up with H2O. Now, what this is going to be known as when you're sharing your electrons to fill your orbits and your valence electrons is something known as a reactant. So reactants are just substances being used to create a chemical reaction. In this case, this would be our reactant. Best way you can remember that is when you add things together, you're reacting them, right? Just like when you're making a cake or baking or cooking, you want to add ingredients together. Those are your reactants. And you're going to end up producing something, which in this case is your product, substances formed at the end of the chemical reaction. So in this case, this would be our product. Now, one cool thing is we do have reversal reactions. So that's when reactants are converted to products, but some products can be converted back into reactants. We do have some reactions that are going to be irreversible. So process in one direction until all the reactants are used up. So again, the main takeaway from this slide is that electrons are going to determine how atoms interact. Remember, electrons want to be, or atoms want to be as stable as possible, so they will donate or share electrons between other atoms in order to achieve that stability. When we do have those interactions, it is going to create molecules. When we have that interaction, that's going to be something known as a reactant, and they're going to end up producing something which is going to be a product. Sometimes we can reverse those reactions, and sometimes they will be irreversible. So that brings us to our next question, which is how do atoms bond to form these molecules? We've talked a lot about electrons. We know that they play a very important role in the production of these molecules, but we need to figure out exactly how, and why is this so important? So again, in order for living organisms to exist, we need to take these small base units and link them together. And when we link them together, we're going to form a bond in order to form those molecules. Okay, to form molecules, we need at least 2 or more atoms to bind together in order to form that. In this case, we have an example of oxygen, or going back to our previous slide, we need our hydrogens and our oxygens, add them together, and we end up with H2O. Again, these hydrogens are looking for 1 electron each. This oxygen is going to be looking for 2. So they're going to be able to help each other out in order to create stability. And when they come together, which that bind will look something more like this, we'll end up making H2O. And as you know, water is going to be incredibly important to living organisms. And as the class goes on, we're going to go ahead and learn more about macromolecules, but our macromolecules are going to be essentially the building blocks to life. We're going to be looking at things like proteins, carbohydrates, lipids, and nucleic acids. So let's go ahead and take a look at our very first bond, which is going to be a covalent bond. And the main thing you want to understand from this is that electrons are going to be shared. Okay, so remember, atoms are looking for stability, and they're going to find that stability with electrons by filling their shells. So they will do whatever they can in order to have that happen. So again, in our covalent bonds, electrons are being shared. Okay, so that means that in this example, we have 2 hydrogens. So we have this one here, and we have our second one here. And remember, they have 1 shell, they have 1 electron, and they're looking for a second to reach that stability. Same thing over here, we have 1 electron, and it's looking for a second. Our oxygen, we have 1, 2, 3, 4, 5, 6, and it's looking for a 7th and an 8th in order to reach that stability. Now, what they're going to do is they're going to go ahead and get together. They're going to help each other out. And you'll notice that we have a sharing of electrons right here. So this right here is going to be our covalent bonds. They're actively sharing the electrons together. This one was looking for 1. This one is looking for 2. Again, they can kind of help each other out. So this one's donating one, this one's getting one, this one's donating one, and this one's getting one. So now they have bonded together and we have created water, or H2O. And what these lines over here are representing are just those connection or bonding points. Okay. So to summarize everything, covalent bonds, electrons are shared. We have an atom of hydrogen, both looking for one additional electron right here and right here. We have oxygen, which is looking for two electrons here and here. So they're going to help each other out. They're going to share or create covalent bonds. So this is sharing its one, this is sharing its one, this is sharing one, and this is sharing one. And because of that, they're coming together. There are no longer three separate atoms, but a molecule of water. Okay. So another thing we didn't know about covalent bonds is that you can definitely share more than one set of electrons. Looking back over here, this is just a singular set of atoms. Right here. I'm sorry, single set of electrons, because they're only sharing this one over here. But again, we can have more than one being shared. And when it comes to that, that's going to be something known as a double bond. So looking at this over here, if you want to go ahead and take an atom of oxygen and an atom of oxygen here, we've identified that this is looking for two electrons, and this is looking for two electrons as well. Because in order to fill its shell, we want a total of 8 electrons. Now, these two can help each other out. In this case, we're going to create a molecule of oxygen or O2. And the way they're going to do that is they're going to create that double bond. They're creating that double bond by sharing the two that they have. Again, this has two and this has two. And they're both looking for an extra one. So they're going to go ahead and get together, share those, and that's how we end up with these two lines in between. We have something known as that double bond. And because of that, we now have a full orbit or full shell. So now that's going to make this molecule of oxygen very stable because, again, they're exactly where they want to be. They have their shells completely filled up. So in their eyes, they are exactly where they want to be. So that's going to summarize covalent bonds. Again, the main idea to take away from this is covalent, they're just sharing. You can have a single bond where they're just sharing one electron, or you can have a double bond where they're sharing more than one set of electrons. Okay, so now we need to go ahead and talk about our very last type of bond, and that's going to be known as an ionic bond. Okay, so when it comes to an ionic bond, what's happening here is they're not sharing anymore. What they're trying to do is one of them is trying to take one. It is not a fan of sharing. So in this case, atoms are going to lose or gain electrons. So down here, this is an example of an ionic bond. You'll notice that we have an atom of sodium and we have an atom of chloride. Now, one important thing is if you look up here at the superscript or the upper right-hand corner, you'll notice that we don't have anything. We don't have a plus or a minus. The reason why we don't have that is because as of right now, the sodium does not have a charge. Because remember, we have our protons, which are positive, we have our neutrons, which don't have a charge, and we have our electrons, which have a negative charge. In this case, because there's no charge over here, our protons are equivalent to the number of electrons, meaning that they're going to cancel each other out. Same thing with this chloride. We have the same amount of protons as we do electrons. Now, when it comes to our ionic bonds, because it's all about our lose and gain, one is gaining, one is losing, you'll notice when we take sodium and chloride, which in this case, it's going to be salt, sodium is actually going to lose an electron, okay? So it's losing an electron and it's being taken by that chloride. This one has one electron in its first shell, so it's not stable. This one has 1, 2, 3, 4, 5, 6, 7. So it's looking for that one other piece in order to feel whole. It's going to take that electron and it's going to end up looking like this. So now our sodium has lost one of those electrons. It's reduced down in one of the orbits, and chloride has completed one of its shells. Now, this is something that's important. You'll notice that our sodium and our chloride now have a plus and now it has a minus. The reason why for this is because now we have more protons, which are positively charged, than we do electrons. So now this is not going to be neutral, and now this is going to have a net positive charge. For our chloride, now we have less protons and we have more electrons. That's giving us our negative charge. Okay, so again, that is going to allow us to create an ionic bond or a compound. And again, whenever you have these, you can create a more positive or negative piece. The last thing I need to mention for this is the formation of ions. So all an ion means is a particle, atom, or molecule that has a net electric charge. Okay, so if we were to take, let's say, lithium, this right here is a neutral element of lithium. If we end up with a positive charge, then we have created an ion of lithium. Again, an ion is just a variation of lithium. It's either going to have a positive or negative charge. So if you see this right here, this is its normal neutral state. If we end up with a positive or a negative, that is going to be an ion of lithium, because that would indicate that it has lost an electron. All right, and just like that, that concludes this lecture. What I'm going to do now is I'm going to give you an opportunity to kind of test your knowledge to see if you can identify the differences between ions, if you can identify the differences between atoms and molecules, what their symbols are, things like that. So I'm going to go ahead and give everybody a moment to pause this, give this a try. All right, welcome back. What I'm going to do now is I'm going to quickly go over some of these so you have an idea of exactly which ones would be what. So what I'm going to do over here is I'm going to go ahead and show you some of the answers. So in number 1, it's asking to look at the following chemical symbols. Which of the following are going to be atoms and which ones are going to be molecules? Now, one way to easily remember this is, remember, a molecule needs to contain at least 2 or more atoms. So in this case, all you're doing is looking for the capital letters. Because remember, whenever you're dealing with an element, it's going to be indicated by a symbol. And that symbol can be in the form of 2 ways. It can either be one capital, in this case, oxygen is going to be a single element, or it might have a capital and a lowercase, just like this over here, which we have a capital and a lower. So if you just follow the rule of look for the capital letters, and that's going to indicate if it's going to be an atom or a molecule, then you should be in a good spot. So just like this, if we go ahead and look at this, we have one capital right here. Oh, I apologize. There is a subscript. So in this case, we have 2 of these. So in this case, it would be a molecule. This one, we have 1, 2 capital. So in this case, it would be a Q. This case, we have capital lowercase. So in this case, it would be atom. And then in this case, capital, capital, capital. So in this case, it would be a molecule. The reason why this is a molecule but only has 1 capital is it's an O2, meaning that it has 2 oxygens. So this is what that would look like. We have 1, 2 capital, so that would be a molecule. Looking at this over here, it says when provided with symbols representative of an atom or a molecule, how can you easily differentiate between the 2 groups? Again, symbols between atoms and molecules. If you're just looking for those capital letters, you should be okay. So again, if we look at something like glucose, we have 6 carbons, 12 hydrogens, 6 oxygens. Again, in order for it to be a molecule, it needs to be more than 1. So in this case, we have 1, 2, 3, and we have tons of variations for it. So this would be a molecule. To kind of like clarify things a little bit more, atoms will only have a singular symbol like that, and they will not have a subscript or a number next to it. So again, in this case, we have an A because we don't have a subscript, because that subscript's identifying how many of these we actually have. So because there's nothing there, it would be just an atom. Same thing with this over here. We have 1 oxygen, no subscript, so then that would just be an atom of oxygen. But if we had an O2, again, that means we have 2 oxygens like this, making it a molecule. All right, looking at number 3, it says, look at the following symbols. Which of the following are atoms and which ones are ions? Remember, atoms are going to be neutral, so they are not going to have a plus or a minus associated with them. Ions, remember, are going to be variations between that. They are going to have a positive or negative. So this one will not have these. This one will. In this case, I'm going to use A for atom, I for ion. We don't have anything over here, so this will be an atom. Over here, we don't have anything over here, so that's going to be an atom. Over here, we have a positive, so that's going to be an ion. We have a negative, so that'll be an ion. This atom, this atom, we have a plus ion. Over here, we have negative, so that's an ion. And then this as well, which is going to be an ion. So the trick for this, again, is to look for a positive and negative. If we do not have one, it's going to equal an atom. If we do have one, it will be an ion. Okay, and then our last one, when provided with chemical symbols represented an atom or an ion, how can you easily differentiate between the two? Again, as long as you look for that plus and minus on the superscript, right? So the number up top here, or the charge, if you see one, it's going to be an ion, and if you do not, it is going to be an atom. And just like that, that is going to conclude our lecture on our chemistry portion. So if you do have any questions, please feel free to ask. I'd be more than happy to answer or clarify any questions you may have. And again, I always encourage you to look at the supplementary material. And again, if I explain this and you're not quite sure or you kind of get it, but you feel like you want a different perspective, you always have Dr. Cass' videos available as well. So you're always more than welcome to watch hers. Okay. Again, if you have any questions, please feel free to reach out. I look forward to seeing you guys in the next lecture.